So Taylor polynomials are the next big idea, and it's a really big shift from what we've been doing so far in Chapter 10. A Taylor polynomial is a polynomial that represents a particular function at a point. And what I mean by representing the function is, it has the same value as the function at that point, it has the same slope as the function at that point, and it has the same third derivative, fourth derivative, depending on how far out my polynomial goes. So we're going to use these polynomials, these new kind of Taylor polynomials, to approximate the value of a function at a different point. So here's how we'll do it. This is a formula for a Taylor polynomial. The degree of the polynomial in this example is k. So that tells us the degree of the polynomial that we're going to use. And we're going to use it to approximate some function near some center, x equals a. So I'm going to kind of go through this a little bit. Each term of our polynomial is going to have a factorial in it, a derivative in it. This notation again means the nth derivative. Oops. And it's going to have an exponent, and those are all going to match. So your factorial, your exponent, and your derivative are all going to be the same for each term. And when you're doing a Taylor polynomial, it's going to start with a 0. So it's going to start with a 0, but what does 0 factorial even mean? If it means 0, then this formula has us dividing by 0, which is a big no-no in math. I don't know much, but I certainly know that. It turns out that 0 factorial means 1, and that's a little bit frustrating to people. And by people, I mean I include myself, because I want 0 factorial to be 0, unless I start thinking about patterns. Like if I go from 1 factorial to 2 factorial, the way I get from 1 to 2 factorial is I multiply by 2. And then if I go to 3 factorial, the way I get from 2 factorial to 3 factorial is I multiply by 3. And if I want to go backwards from 3 factorial to 2, I would divide by 3. If I want to go backwards from 2 factorial to 1, I would divide by 3. If I want to go backwards from 1 factorial to 0 factorial, I'm going to not divide by 3. I lied. Divide by 2. You knew what I meant, right? So if I want to go backwards from 2 factorial to 1 factorial, I'm going to divide by 2. If I want to go backwards from 1 factorial to 0 factorial, then what I should be doing is dividing by 1. So I'm going to take 1 factorial divided by 1, and that's going to give me 0 factorial. So that's why 0 factorial is 1. It's a little bit frustrating, but it allows us to continue the factorial pattern all the way to 0. We can't continue it any further. We're not going to go any more negative, but that's because at that point, that's when we'd be dividing by 0, and that's not okay. So we stop at 0, and that's our first factorial. Okay. All right, so anyway, let's say I would like to write a 4th degree Taylor polynomial for some function x. What that means is I'm going to start at 0, and I would take the 0th derivative. The 0th derivative would be the function itself. I'm going to plug in a to that function, and I'll get a value. And then I'm going to divide by 0 factorial, which is 1. And then I'm going to do x minus a to the 0 power. Well, I don't need to write all that stuff down, because to the 0 power would just be 1, and 0 factorial is just 1, so I would start with f of a only. All that other stuff kind of doesn't matter. So I have f of a. That's my constant term. Remember, f of a is a number. We've plugged our number in, and we have a number value for f of a. Then because this is a sum, we're going to have plus, and then our next one would be the first derivative divided by 1 factorial, which would be 1. So we're going to have the first derivative. We're going to evaluate it at a. That's going to give us our coefficient. And then we do need to write x minus a because that would be to the 1 power. Our next term would be the next derivative. So we're going to take the second derivative, evaluate it at a, and this time we're going to divide by 2 factorial, which is just 2. Stop! And then we'd have x minus a squared. I want to go out to the 4th exponent, so I'm only on 2, so I'm going to have to do the third derivative, evaluated at a, divided by 3 factorial, which is 6, and then x minus a to the 3rd power. And then I'm going to do the 4th derivative. We don't write 4 tick marks, we write a 4 in parentheses. We're going to evaluate that at a. We'll divide by 4 factorial, and then we'll do x minus a to the 4th power. This is the 4th degree Taylor polynomial for some function. I just kind of wanted to go through what that means as we look at that notation. In class, I had you figure out why these factorials are here, and it has to do with, as we're taking derivatives, we keep bringing down the exponent. So we bring down a 4, we bring down a 3, we bring down a 2, and so we need to divide by that factorial as we're going. All right, so this polynomial is going to have the same value of the function at a, because if I plug in a here, these all go away, so it's going to have the exact same value of the function at a. It's going to have the same first derivative as the function at a. It's going to have the same second derivative, third derivative, and 4th derivative as the function at a. It doesn't necessarily have the same 5th derivative because our polynomial stopped at 4. All right. So here is a Taylor polynomial for some function. What is the center and what is the degree for this Taylor polynomial? So if we go back to this, our degree is going to be how far out we went. So we stopped at the degree k. So we stopped at the degree is 4. And then the center, because that formula has an x minus a in it, the center would be negative 3. All right. James, by the way, Brooke Taylor didn't invent Taylor polynomials. The guy who did was James Gregory, but I think Brooke Taylor was rich, and I think that he stole them from James Gregory, but I actually haven't researched it that much. Okay, now we're going to actually go through the process of constructing a second degree Taylor polynomial. So what we're going to do is, and this section, you're going to be doing a ton of derivatives. So we're going to start with, stop doing that. F of x is the square root of x, or x to the 1/2. F prime of x would be 1/2 x to the negative 1/2. And I'm going to stop at 2 because I'm doing a second degree. Now I want it to be centered at 4, so I'm going to plug 4 into all of these derivatives and the value of the function. So the square root of 4 is 2. 1/2 times 1 over the square root of 4 would be 1/4. And the second derivative at 4 would be negative 1/4 times 1 over square root of 4 cubed. So I would do the square root first because that's easier. And so then I have negative 1/4 times 1/8, or negative 132. Okay, now I'm ready. I have my numbers. Now I'm ready to plug it into the second degree Taylor polynomial. So the first thing I have would be 2, because that's my constant term, plus f prime is 1/4, and then x minus 4, because that's our center, to the 1 power. And now I'm going to do minus 132 divided by 2 factorial, and then x minus 4 squared. 2 factorial is just 2, so my polynomial winds up being 2 plus 1/4 x minus 4 minus 1/64 x minus 4 squared. This polynomial represents the function square root of x when you're close to x equals 4. If you're exactly at x equals 4, it would be equal to the square root of x because it would have the same slope, the same second derivative, and the same value as the function. But as you move out away from 4, it gets to be a less good approximation of the square root function. All right. Last example has a new term in it, Maclaurin. If you see Maclaurin polynomial, that means it's centered at 0. I don't know why Maclaurin gets to have his own name on Taylor series that are Taylor polynomials that are centered just at 0, but he does, so that's how it's going to work. Right? We want a third degree, so we need to start with f of x equals sign. We need to take 3 derivatives. We need to evaluate all of those at our center, which is 0 because it's Maclaurin. Sine of 0 would be 0. Cosine of 0 would be 1. Sine of 0 would be 0. And negative cosine of 0 would be negative 1. Okay, now we're going to start our Maclaurin, our Taylor series. So we're going to do p sub 3 because we want a third degree polynomial. We're going to start with our constant term, which is 0. Our linear term, which is 1 times x, x minus 0. And then plus 0 times x squared minus, this is actually 0 over 2 factorial, minus 1 over 3 factorial times x to the third. So if I multiply this out a little bit and simplify and make things look pretty, I have x minus 1/6 x to the third. And that represents the sine function because it has the same first derivative, second derivative, value, and third derivative as the sine function as long as we're close to 0. All right. I hope this helps with writing Taylor series. Thanks so much. Bye.